I want to give you a framework for understanding what is going to be presented in Chapter 3. And the way I think of Chapter 3 as filling the toolbox, basically looking at the hydrodynamics of flow through porous media and laying out all the tools you need to have to predict flow through porous media and understand it. We start with a capillary tube, solving what's called the Poiseuille equation, where we basically show that the flow through a capillary tube is proportional to the fourth power of the radius and the pressure gradient. And so in that way, we identify the basic capillary flow processes, and the specific flux, which is just the flow divided by the area, is then proportional to r squared times the pressure gradient. Okay. Now, this all applies for Reynolds number equals to 1. And so we basically, out of this, get exactly Darcy's law is going to be the negative of the area times the saturated conductivity times the gradient in pressure, if you will. Okay? And then here we'd have a rho GH. Okay, so we get Darcy's law. Now the trick with Darcy's law is it's all fine and well for saturated systems, so long as Reynolds number is less than 1, but what happens in unsaturated systems? So what if we have K is a function of moisture content? And what we show is that that works just fine. Buckingham said that, and identified, that the equation can be employed whether or not K is a constant at K sat, or if you're using moisture content as something to change the hydraulic conductivity. And we see as the hydraulic conductivity, you take your data and plot up hydraulic conductivity, the maximum value you can take on is K sat, and then it can go down to at theta residual, the conductivity goes to 0. So if this, on this axis is K, this is going to be K sat, and that's how K is a function of theta. So now we have the hydraulic conductivity function, and so yes, we can still use Darcy's law in this way. The one thing is that if you have a flow through an unsaturated system, the water content can change, so the flow in is not necessarily equal to the flow out. And that's a key distinction between saturated and unsaturated media. So we then have to add conservation of mass, and with the conservation of mass, we end up with the governing equation, which we call the Richardson-Richards equation. And so that's the governing equation for our system. There's a few nuances that are really important as we upscale. So we've been thinking about this whole problem in a capillary tube, but what happens when the soil is layered? Then the conductivity might be different in the two directions, and what we show is that the conductivity here that shows up in Darcy's law ends up being not a scalar, but actually a tensor. And so that's an important little piece. So it becomes a tensor. Otherwise, we point out that, that Darcy's law works fine as long as you're in the Reynolds number less than 1. And if you get too low a flow, then the conductivity also goes slightly nonlinear. So we talk a little bit about the nuances there. But basically, we have the framework, and we look at the physics then. So with upscaling, we then look at the physics. And by looking at the physics through what we call Miller scaling, then we can actually make cool predictions, whereas we know the particle size, and we know the viscosity of water, and we know the surface tension of the fluid, then we can translate between systems and actually predict these curves as a function of the physical properties of the media. And this is really important when you're looking at how oil moves or how textural changes in the soil might affect the actual infiltration. So finally, we have the framework laid out, and then we apply it to basic problems in infiltration, evaporation, and preferential flow. And then finally, at the end of the chapter, we give you some methods by which you can measure these properties in the laboratory and in the field so that you can fill your toolbox with all the tools required to quantitatively predict the movement of water and other fluids in porous media.